Welcome back to The Deep Dive. I'm your host, and today, wow, we're stepping into a world that honestly sounds straight out of science fiction. Imagine playing a video game, right? But instead of just experiencing a world someone else built, you're actually generating it on the fly, editing its underlying structures, changing the entire visual style with just like a simple prompt and seeing it all respond in real time. And not just kind of okay visuals, but with the incredible fidelity you'd expect from, a blockbuster title. That's the pretty transformative frontier we're diving into today.
That's a great way to frame it. Yeah, we're taking a really in-depth exploration into Yan today. It's a groundbreaking foundational framework for interactive video generation. And like you said, this isn't just about creating videos that look nice. It's about dynamically building and manipulating entire interactive digital worlds in real time with a level of fluidity that's, well, pretty unprecedented.
So, our mission for this deep dive, as usual, is to really unpack the intricate technical details. We want to look at the innovative implications of Yan's core modules. We want to understand precisely how it pushes the boundaries of AI-generated content. And as always, our focus is going to be strictly on the technical architecture, its performance, its capabilities. We'll be steering clear of the ethical or inclusivity discussions today. We really want to dig into what the papers talk about, the nuts and bolts, and maybe even touch on what they don't fully delve into, technically speaking.
Right. And Yan, at its heart, is this really comprehensive system. It's not just one trick. It seamlessly integrates three fundamental pillars. You've got AAA level simulation, think smooth physics, believable interactions. Then there's multimodal generation, so it responds to different kinds of inputs, text, images, you name it. And finally, multi-granularity editing, letting you make detailed changes on the fly. These all work together in concert to create these truly dynamic and customizable interactive experiences.
And just a reminder to stay updated on all the latest cutting-edge AI and ML research papers, you can visit our webpage, neuralintal.org. And make sure to check us out on YouTube as well. You really won't want to miss what's coming next in the world of AI breakthroughs, the dawn of interactive generative video, IGV, and Yan's vision. So we've been on quite a journey with AI-generated content, or AIGC, haven't we? Over the past few years especially. I mean, it started with text, generating articles and stories. Then it moved to crafting these incredibly realistic static images, mind-blowing stuff. And more recently, we've seen these impressive leaps in synthesizing video. But now it really feels like there's a new, profoundly different frontier emerging. We seem to be moving from just, watching AI create to actually interacting with its creations in real time.
That's a perfect way to put it, yeah. This new frontier is what we're calling interactive generative video, or IGV. And the key distinction here, the thing that really sets it apart, is that unlike conventional video generation where, the content is fixed once it's made, IGV dynamically responds to user inputs. It enables these real-time personalized visual experiences that truly put you, the user, in the driver's seat. You're not just a passive observer anymore. And what's truly fascinating about this, what makes it a potential, genuine game changer, is its power to revolutionize fields that really demand ongoing human-AI interaction. Think about immersive media VR, AR, where you're not just a spectator but an active participant. Or the next generation of virtual simulation environments, maybe for training or scientific exploration. And even advanced embodied intelligence systems. Imagine AI agents learning and operating within these fluid, dynamically generated worlds. The ability for the AI to react in real time with such high fidelity just fundamentally changes how we can conceive of digital interaction. It's moving from passive consumption to this active, real-time co-creation of digital realities. It's huge.
Okay, let's unpack this a bit more then. Before Yan came along and sort of tried to unify all these different elements, what were the big challenges? What was holding back IGV from truly reaching this revolutionary potential? What were the critical gaps researchers were really struggling to bridge all at the same time?
Right. Before Yan, existing methods face some pretty considerable hurdles. They often struggle to address three critical gaps simultaneously. It's like trying to build a really sophisticated race car, but you can only focus on the engine or the aerodynamics or the tires, but not all at once. So first, there was the massive challenge of achieving high-fidelity, real-time visuals. And we're talking quality comparable to modern video games here, 1080p resolution running at a smooth 60 frames per second. And crucially, coupled with intricate, believable physics simulation. A lot of the existing approaches, well, they were limited to much lower resolutions, maybe 720p or even less, or lower frame rates, which made them feel kind of clunky, less immersive, almost like watching a low-quality stream sometimes. And very often they lacked accurate physics engines, which led to less believable or sometimes just plain buggy interactions. Things wouldn't behave right. Second, there was the real difficulty in achieving generalizable and prompt controllable generation. It was incredibly hard to generate content that was both diverse enough, covering lots of different domains, say from a fantasy forest to a futuristic cityscape, and precisely controllable by different kinds of user prompts, whether that's text descriptions or maybe reference images. Systems would often get good at one thing, like maybe generating landscapes, but then struggle to generalize or respond to really nuanced commands, or they'd be terrible at generating characters, for example. Getting both breadth and control was tough. And finally, a really crucial gap, maybe the most crucial for this interactive element, was dynamic interactive editing. Most previous methods treated interactive video generation like creating a fixed piece of content, even if it could respond to some basic input. But users couldn't dynamically modify the generated environment or its elements during an interaction session. It was like having a fantastic Play-Doh set, right? But once you molded something, you couldn't just change its color or shape on the fly without starting all over again. Yan specifically sets out to enable that on-the-fly content customization, which is just a massive leap forward for genuine creativity and interaction.
So it sounds like looking at that prior work, they often had to pick one of those challenges to focus on, right? And then they'd inevitably struggle with the others. You mentioned systems like Game Engine or PlayGen. They offered some interactive bits, but maybe the visuals weren't great or they weren't very versatile.
Exactly. Limited visual quality, limited generalizability.
And then others like The Matrix or Game Factory, they made strides in maybe the generative worlds part, but then fell short on the complex physics simulation, or crucially, couldn't keep up that real-time performance at high resolutions. So Yan is really designed to tackle all of these challenges simultaneously, to create a truly unified, powerful framework. It's not just a toolbox, it's like an integrated workbench.
That's exactly it. That's the core idea. Yan is conceived as this foundational framework covering the entire pipeline, soup to nuts, from the initial simulation and content generation all the way through to real-time editing. And it's composed of 3 deeply integrated core modules, each one tackling one of those critical challenges we just discussed. What's particularly significant, I think, is that all these modules are trained on a shared, high-quality dataset. It's derived from modern 3D game environments. They specifically mention a game called Yuanmeng Star. Oh, this shared foundation is absolutely key to their seamless integration. It's like all the different parts of the engine are speaking the same underlying language, trained on the same reality, if you will. So the 3 modules are, first, YanSim. This is the powerhouse responsible for delivering that AAA-level simulation we talked about, the smooth motion, the realistic physics, the responsiveness. Second, YanGen. This enables multimodal content generation, allowing for diverse and prompt-controllable world creation, building the worlds. And third, YanEdit. This provides the multi-granularity editing capabilities, allowing users to modify content and style dynamically on the fly. This whole coherent end-to-end workflow is explicitly designed to move interactive video generation beyond just fragmented prototypes, where you might have one tool for generation and maybe another clunky one for basic editing. It aims for a truly unified generative paradigm that handles everything within a single integrated framework. It's about building a holistic, AI-driven interactive creation engine from the ground up.
The engine for AAA-level real-time simulation.
Okay, so let's dig into YanSim first. This is the engine, right? The part tackling that huge first challenge, achieving AAA-level simulation. We're talking 1080p resolution, 60 frames per second, smooth as butter with complex mechanics. That's an incredibly demanding real-time performance target. For those of us who like to peek under the hood, how exactly do they manage to pull off such a feat? What's the core engineering magic here that allows for this kind of demanding real-time interaction?
Yeah, pulling off that performance is definitely where a lot of the magic happens. The ingenuity behind YanSim's real-time capability lies in a really sophisticated combination of techniques. Their approach centers on 2 main components working together. First, they developed a highly compressed, low-latency 3D variational autoencoder, or VAE. Now think of a VAE as a kind of brilliant data compressor and decompressor. Specifically for visual data like images or video frames, it allows the system to work with much smaller, much more manageable versions of the visual data, dramatically reducing the sheer volume the AI needs to process frame by frame, but hopefully without losing the critical visual information. It shrinks the problem down. Second, they use something called a KV cache-based shift window denoising inference process. That's a bit of a mouthful, but...
All right, break that down a bit. KV cache,
Yeah.
shift window.
Okay, yeah. So the KV cache is essentially a clever memory trick. Imagine you're trying to predict the next few notes in a song really quickly. The KV cache helps the AI efficiently remember and access the melody and rhythm it just played, the key, K and value V information from recent computations. This enables it to predict what comes next very quickly and keep the music, or in this case the video, flowing seamlessly without recomputing everything from scratch. The shift window part refers to how it focuses its attention locally in time, making it faster. These components are meticulously engineered to work in tandem. So the VAE efficiently condenses the raw image data into this much smaller latent representation, significantly cutting down the amount of data the main diffusion model needs to process. Then the KV cache and shift window denoising let that diffusion model predict future frames autoregressively one after another and with very low latency. This whole setup allows the system to translate user actions into interactive visuals at a performance level that truly mirrors that of a high-end commercial game engine. It's fast and efficient.
Okay, that gives us the high-level view. Now let's really get under the hood of YANSIM itself. We know it builds upon stable diffusion, right? Which is a pretty well-established, powerful generative model architecture. But stable diffusion wasn't originally designed for this kind of real-time interactive stuff. So what key modifications were absolutely crucial for its efficiency, especially when handling these dynamic in-game interactions where every millisecond counts? They must have had to really tweak the model's DNA.
They certainly did. Yeah, adapting stable diffusion for this task required some critical modifications, really focusing on speed and interactivity. There were two main areas of architectural adaptation that stand out. First, the VAE design was optimized for enhanced compression and speed. The core idea here was to shrink the video data much more aggressively than usual before the main AI model even sees it. They significantly increased the spatial compression. They did this by augmenting the VAE encoder with extra downsampling layers, boosting the spatial downsampling factor quite a bit, from the standard 8x to 32x, so much smaller representations. They also introduced temporal compression, essentially bundling consecutive video frames together more tightly along the channel dimension, achieving a temporal downsampling factor of 2. Now, to handle this much denser, more compressed information packed into each little piece of data, they had to expand the internal capacity, the channel dimension C, of the latent tokens to 16. And crucially, for inference speed making it run fast, they made the decoder part, the part that turns the compressed data back into the final image, very lightweight. They actually pruned layers from it, but they balanced this by adding other layers to maintain alignment with the encoder's downscaling factor. This entire optimization process struck a very careful balance. Get maximum compression for speed, but without sacrificing too much visual quality, which is obviously paramount for that 60 FPS target at 1080p. Second, the diffusion model design was specifically adapted for autoregressive inference. This is really where the real-time frame-by-frame generation comes into play. The diffusion model now includes three distinct types of attention blocks. You've got spatial attention, which helps the model understand relationships within a single frame, making sure things look coherent, textures line up, that kind of thing. Then, really vital for interactivity, there's action cross attention. This is where user actions like you pressing a jump button get translated into a numerical signal, a token, and are directly injected into the model's processing. This is how the model directly links your input to the on-screen action, making the character actually jump when you tell it to. And finally, they introduce 1D causal temporal attention. This is absolutely key. Causal here means that the AI, when it's predicting the current frame, say frame FT, can only look at information from previous frames, FTT. It can't peek into the future. This causal structure is essential for iterative frame-by-frame prediction. It's what underpins the real-time interactivity and the low latency generation. It directly distinguishes YANSIM from standard fixed-length bidirectional diffusion models, which generate a whole sequence at once and therefore can't react dynamically to input mid-sequence.
Wow, okay, that's a serious deep dive into the architecture itself. Now, training models this complex, and then actually making them run consistently at 60 FPS in real time. That isn't just about smart design choices, right? It must involve some really clever engineering at every single stage. What does that look like? Both in terms of the training process itself and then all the optimizations they have to bake in to achieve that kind of blistering inference speed.
You're absolutely right. Achieving that peak performance, that 60 FPS target, is definitely a multi-layered engineering feat. It involves both how they train it and how they run it. So starting with the training stages, it's a careful two-phase approach. First, there's the VAE training. Here, the VAE learns how to efficiently compress and then decompress pairs of consecutive video frames. This stage is optimized using a combined loss function looking at both mean squared error, pixel-level accuracy, and LPIPS, perceptual similarity, to ensure the regenerated frames not only match the original pixels closely, but also look good and natural to the human eye. Second is the diffusion model training. They use a specific strategy called diffusion forcing, which is designed specifically for this kind of autoregressive inference where the model predicts frames one after another based on previous ones. What's clever here is how they handle the input during training. While most frames in a training video clip have noise added, as is standard in diffusion models, the very first frame is kept clean, acting as a clear ground truth starting point for the model to learn from. Then, during training, the noise levels progressively increase along the time axis of the clip.
Yeah.
This mimics the real-time inference process where the model has to denoise based on its own potentially slightly noisy previous outputs. It helps the model become more robust at denoising from various levels of imperfection. Now, moving on to the inference optimizations for speed, this is where a lot of that AAA level performance is really eked out. They achieve significant sampler efficiency by using a DDIM sampler, which drastically reduces the number of denoising steps needed for each frame down to just 4. That's a huge reduction, minimizing computational while, they claim, still preserving visual quality.
Only 4 steps. Wow.
Yeah, very few steps compared to standard diffusion. Then on the hardware level, they implemented several critical optimizations. They applied structural pruning to the UNet architecture, that's like trimming unnecessary connections or pathways in the neural network to make it leaner and faster. They also utilized FP8 quantization for both weights and activations in matrix multiplication operations. FP8 is a smaller, more efficient numerical format than the standard FP16 or FP32. Think of it like switching from using high-precision scientific notation for calculations to using simpler whole numbers or basic fractions for quick mental math. It's much faster, and for graphics, the slight loss in precision often isn't noticeable to the eye. This alone, they report, delivers a 1.5x to 2x speedup over FP16 and contributes significantly overall. They also captured the entire inference pipeline, VAE decoding, diffusion step, VAE encoding as a single COD graph. This eliminates the small overhead delays that occur when launching individual computation kernels sequentially on the GPU. It bundles everything together. They developed custom kernels using Triton, a language for GPU programming, to optimize things like thread block geometry and memory access patterns, squeezing maximum efficiency out of the specific hardware. And finally, leveraging torch.compile with the max autotune mode automatically applies many of these kinds of low-level hardware-specific optimizations, providing yet another significant performance boost, around 1.15x, they say. And one more trick to further reduce latency. They employ parallel processing. The two main models, the VAE and the diffusion model, are actually deployed on separate GPUs. They use a clever queue system to transfer the generated latents, the compressed representations, between the GPUs. This avoids any potential slowdown or bottleneck that would arise from having them wait on each other if they are running serially on the same processor. It's really a complete system optimization from the model design through the training strategy all the way down to the hardware deployment, all geared towards hitting those demanding 60 frames per second.
Okay, this is where it gets really interesting for the user experience, right? All these incredibly intricate technical innovations of the super compressed VAE, the causal temporal attention, the FP8 quantization, running things in parallel on multiple GPUs. How does that actually translate into what you, the user, sitting there with a controller or keyboard, actually experience? What's the proof in the pudding, so to speak, for Yen Sim's claimed AAA level capabilities?
Right, the proof is definitely in the experience. Does it feel like a high-end game, or does it feel like a clunky tech demo? They evaluated Yen Sim across 4 key dimensions, and the results they present are pretty compelling. First, in terms of visual quality, Yen Sim successfully renders intricate details across a wide range of artistic styles, faithfully reproducing diverse visuals from the training game Yuanmeng Star at that target 1080p resolution and high FPS. If you look at the examples they provide in the paper, you can see these vibrant, dynamic environments, lush grasslands, futuristic cityscapes with really clear details. It's not just generating blurry approximations, it's rendering with impressive fidelity even during motion. Second, and absolutely paramount for any interactive system, is motion consistency. Yen Sim accurately responds to frame-level action signals. So when you press a button, it generates precise and immediate feedback in the subsequent frames. This responsiveness, combined with the high FPS and the low latency achieved through all those optimizations, creates an experience that closely mirrors real gameplay. For instance, they show a husky-like character moving smoothly through a complex scene. Every input seems to translate into a believable movement without noticeable lag or visual stutter. It feels connected to your input, which is absolutely crucial for immersion. Third, and this is critical for realism beyond just pretty pictures, is accurate mechanism simulation. The system realistically reproduces physical characteristics and interactions within the generated world. We see examples like a character sliding down a water slide. Yen's sim captures the natural inertia and momentum you'd expect. Another example shows a character touching an electric fence and being visibly affected, unable to move, demonstrating accurate collision response and environmental effects. Or a character jumping higher when they land on a trampoline, showcasing an understanding of material properties and energy transfer. This goes beyond just visual rendering. It indicates a deeper understanding of the world's underlying physics and how objects should behave. It's simulating the rules of the world, not just its appearance. And finally, there's the long video generation capability. Despite the complexity and the real-time interaction, YanSim can generate long interactive videos, potentially indefinitely, with consistently high visual quality maintained throughout. This validates its ability to produce continuous, high-quality content without noticeable degradation over extended play sessions. You're not going to see the world suddenly fall apart or get blurry after playing for a minute or two. It holds up.
That sounds like a massive leap, especially in resolution and frame rate, compared to what we've typically seen in this generative video space before. I mean, moving from maybe 720p or often even lower resolutions, maybe at 15 or 30 FPS, up to a full 1080p at 60 FPS for an interactive experience that's a monumental difference in perceived quality and smoothness. YanSim really seems to stand out there, delivering potentially infinite video length at this high quality with low latency, far exceeding the specs of prior works like PlayGen or Genie. That performance differential alone is substantial and fundamentally changes the kind of interactive experiences that are even possible to generate convincingly.
Multimodal world generation.
Okay, so YanSim gave us this incredible engine, right? Capable of simulating these AAA-level interactive experiences with impressive fidelity and responsiveness. But an engine needs a world to power. It needs content. And that's where Yangen steps in, introducing the capability to generate entire interactive worlds using multimodal inputs, text, images. Building and expanding these worlds dynamically, though, that presents its own set of really fascinating challenges, doesn't it? Especially when it comes to keeping them consistent and coherent over long interactive sessions. You mentioned this problem earlier, but tell us more about semantic drift. Why is this such a persistent headache for these kinds of generative AI models?
Oh, it's a huge headache. Yeah, it's a fundamental challenge for pretty much any autoregressive generative model, especially those dealing with complex sequences like video. Semantic drift, put simply, is when the generated content gradually starts to, well, lose its way. It drifts away from the initial prompt or the established context. Imagine you tell an artist, paint me a serene forest scene. They paint a beautiful tree. Then you ask them to paint what's next to that tree, but critically, they can only look at their own most recent brushstrokes, not your original request or the overall scene plan. If they make even a tiny mistake or inconsistency in that next brushstroke, maybe the lighting is slightly off, or the style changes subtly, that mistake gets carried forward and baked into the next set of brushstrokes, and then the next. Pretty soon, your serene forest might start looking like a chaotic jungle, or maybe even morph into a desert, because these small errors accumulate and compound over time. This arises from two main related issues: error accumulation, like we just described, and something called exposure bias. Exposure bias means that during training, the model usually sees perfect ground truth previous frames, but during inference, it has to generate based on its own previous outputs, which might be imperfect. It's not exposed to its own potential mistakes during training. So, as an autoregressive model predicts future frames based on its own potentially flawed prior outputs, any small errors or inconsistencies can compound dramatically. These errors don't just disappear, they're fed back into the model as the basis for the next prediction. Over a long sequence, this inevitably results in a degradation of visual quality and, critically for interactive worlds, a loss of both temporal consistency, things changing inexplicably over time, and spatial consistency, the layout of the world becoming unstable or nonsensical. In an interactive environment where the world absolutely needs to remain stable and coherent as a character moves through it over potentially long periods, this drift is completely unacceptable. It utterly breaks the illusion of a persistent, believable digital world. It's like the world is slowly forgetting what it's supposed to be, frame by frame.
Right, the world literally starts losing its mind as you play. That's a critical problem to solve if you want long-term engagement. So what does this mean for actually keeping these generated worlds consistent over time? How do you prevent that dreaded semantic drift? Yangen introduces something called hierarchical captioning. Can you break down how this dual context strategy works? How does it maintain both a stable global reference and those detailed local descriptions? It sounds like they're giving the AI a much more sophisticated set of instructions to follow.
Hierarchical captioning is indeed Jan Gen's elegant solution, or at least proposed solution, to this semantic drift problem. It's a clever dual context strategy designed specifically to provide the generative model with both a stable, overarching global reference and highly detailed, time-sensitive local descriptions. The goal is to ensure coherence across different scales, both the big picture and the immediate details. So the first level is global captioning. You can imagine this as a comprehensive, unchanging blueprint or maybe a world map for the entire interactive environment being generated. A single detailed global caption is generated for an entire interactive world, usually based on analyzing an extended traversal video of that world, maybe about a minute long. This global caption captures the world's essentially unchanging characteristics, its overall layout and topology, like where are the main regions, what's the general shape, its core visual theme, the color palette, dominant materials, architectural style, and the base lighting and weather conditions that are supposed to be consistent throughout. This global caption acts as a constant anchor, a persistent point of reference for the entire generation process. By constantly reminding the model of this unchanging global context, it explicitly aims to prevent that long-term semantic drift. It ensures that the fundamental identity of the generated world, it's a cyberpunk city at night, for example, remains consistent even as the user interacts within it for extended periods. The AI always remembers the big picture. Then the second level is local captioning. For each short segment of the video, typically around 3 seconds long, a much more detailed local caption is generated. This focuses specifically on describing the transient, dynamic events occurring within that very specific, narrow time window. You can think of this as the street view level of detail, or information about specific points of interest right in front of you. This includes describing the immediate surroundings visible within the camera's view at that moment, any interactive objects whose state is changing, like a door opening, a platform moving, an item being picked up, and any critical gameplay events happening right then, such as the character dying or completing a specific task. This highly detailed, time-sensitive local information is crucial for ensuring that all the fine-grained details are rendered with high fidelity and align precisely with the ongoing moment-to-moment interaction. And technically, to generate these captions at scale, they leveraged Qwen 2.5 VL, which is a powerful large vision language model. They used it to label an enormous dataset, 98 million frames for training Yangen. So this dual context approach is fundamental. The global caption maintains the world's overarching identity and prevents long-term drift, while the local captions ensure the dynamic, frame-by-frame details are accurate, responsive, and relevant to what's happening right now.
That hierarchical captioning strategy sounds incredibly powerful for maintaining coherence. It makes a lot of sense. But now, how is this meticulously structured information, these global and local descriptions, actually integrated into the training pipeline? How do they use it to enable this real-time, open-ended generation of interactive worlds? It sounds like it must be a pretty complex dance of data conditioning and different model training stages, each building carefully on the last one.
It is indeed a complex, multi-stage training pipeline. They visualize it quite clearly in Figure 8 of the paper, actually. It's carefully designed to convert a base generation model into a real-time, causal, autoregressive generator that's capable of potentially endless interaction. So the first stage is all about building the foundational world generation model, conditioned on multimodal inputs. They start by adapting an existing pre-trained model called WAN. WAN is already pretty good at using cross-attention for handling text and image conditions. They fine-tune this WAN model using a technique called low-rank adaptation, or LoRa. LoRa is a very efficient method for adapting these huge pre-trained models to new specific tasks without having to retrain absolutely everything from scratch. It's like adding a small, specialized adapter onto a powerful general-purpose tool, making it good at a new job quickly. Crucially, those hierarchical captions we just discussed, both the global and the local ones, concatenated together, are used as dense supervision signals during this fine-tuning. This explicitly tackles that anti-drifting problem by giving the model rich, continuous context about both the overall world and the immediate situation. They also add a clever training trick. With a small probability, maybe 10% of the time, PO 0.1, they only provide the global caption. This forces the model to learn how to generate plausible sequences even when it only has minimal high-level guidance. It makes it more robust for situations where local details might be sparse or less critical. Okay, the second stage involves integrating the action-based conditions. This is where the interactivity really comes in. An interactive module is introduced and specifically trained to incorporate user action signals directly into the generation process. This module uses a relatively simple yet they found effective action encoder. The encoded action sequences are then injected into each block of the main generative model, which uses a DIT or diffusion transformer architecture via a separate cross-attention layer. This is the mechanism by which your user input pressing forward, jumping directly guides the flow matching process, influencing how the world generates in response. A really key design choice here is that all the other parameters in the main model remain frozen during the specific training phase. This is important because it ensures that the interactive module learns a style-independent control mapping. The goal is for the actions to work consistently, regardless of whether you're generating a cartoon world or a photorealistic one, which is vital for better generalization across diverse generated worlds. An attention mask, similar to the one used back in YanSim, enforces action causality, meaning an action taken now only affects future frames, not past ones. And again, to improve robustness, null actions, representing no input, are randomly substituted during training, with P 0.1. This helps the model handle periods of inactivity and also enables something called classifier-free guidance, which can improve generation quality. The model here is trained to predict velocity using rectified flows. Rectified flows are a newer technique that aims to make the path from random noise to a clean image more direct and efficient than traditional diffusion paths. The loss function then minimizes the squared difference between the model's predicted velocities and the true velocities, how things should move, conditioned on all the inputs, text, image, and action embeddings. The third stage is autoregressive post-training for infinite generation. This is where they convert the model into a highly efficient, few-step causal generator suitable for real-time use. It begins with something called autoregressive initialization. They collect prompts and then perform multi-step denoising using the rectified flows framework to generate what are called OD trajectories, basically, paths showing how an image evolves from noise to a clean state over several steps. From these trajectories, a specific subset of noise samples is selected to train a very efficient four-step generator. Yangen is then explicitly modified into a causal model. They achieve this by employing block causal attention within its self-attention layers. This is critical because it structurally enforces that each token representing a part of a frame can only attend to tokens from prior frames, enabling that real-time iterative prediction necessary for live interaction. This causal Yangen version is then trained on the four-step ODE trajectory dataset using that diffusion forcing paradigm again, with a regression loss comparing its outputs directly to the clean, grand truth latent representations. And finally, the fourth stage involves self-forcing post-training for even more efficient inference, which is essentially a distillation process. They use distribution matching distillation, DMD.
Distillation, like making the model smaller and faster.
Exactly. DMD is used to extract a highly efficient few-step generator from the more complex trained model. DMD works by minimizing the statistical difference, the KL divergence, between the distribution of images the generator produces and the distribution of real data. Furthermore, they use a technique called self-forcing. Instead of always showing the model the correct next step from the training data, which is called teacher forcing, self-forcing trains the generator using an autoregressive approach where it generates its own training samples by predicting sequences based on its previous outputs. This is a clever way to help reduce the accumulation of errors that can sometimes happen with traditional teacher forcing, because the model learns to cope with the imperfections inherent in generating sequences based on its own, potentially slightly flawed, previous steps. It becomes more robust to its own mistakes, which is vital for long generative loops. So what's the impressive result of all this sophisticated multi-stage training? After all this post-training and distillation, Yangen achieves real-time interaction at a respectable 12 to 17 frames per second on a single NVIDIA H20 GPU. And what's even more impressive is that it scales pretty well. They show it reaching a smooth 30 FPS using 4 NVIDIA H20s working together with unified sequence parallel inference. This entire complex pipeline enables real-time, potentially infinite content generation that responds dynamically to action signals and can even adapt the content on the fly by switching the text or image prompts during interaction.
Wow, okay. So with all these incredibly complex technical mechanisms firing on all cylinders, the hierarchical captioning, keeping things coherent, the multi-stage training pipeline, building up the capabilities step by step, the distillation, making it fast enough for real time,
What kind of actual interactive experiences can Yangen create for users? What's the output of all this intense engineering? What does this mean for someone sitting down wanting to play or create within these generated worlds?
It means they get access to some remarkable and versatile capabilities, allowing for truly dynamic and interactive world creation that really goes far beyond what we've typically seen before from purely generative systems. The paper showcases several key areas. First, there's text-guided expansion. This is vividly illustrated in Figure 11 of their paper. Users can dynamically expand or morph a scene during the interaction just by providing modified textual descriptors. For example, they show an original disco-themed environment smoothly expanding and transforming into a classical musician scene based on a new text prompt. What's crucial here, and really impressive, is that this expansion maintained a strong sense of continuity. It does this by preserving shared structural elements, like specific tiling patterns on the floor or the color of certain platforms, even as the overall theme changes. This facilitates what they cleverly call cross-domain scene morphogenesis, where different themes can seamlessly blend and evolve from one another without jarring, sudden cuts. The system also demonstrates an ability to synthesize physics-aligned actions, maintain spatial reasoning, and even adaptively negotiate obstacles within these evolving text-driven environments. It's almost like having an AI director who can subtly change the set design in the middle of a play, and the actors, the interactive elements, still know exactly what to do and where to go. Next up, and equally cool, is image to interaction. You can see examples of this in Figure 12. Yangen can seamlessly generate and respond within diverse open-world scenarios based on just an initial reference image provided by the user. So whether you give it an image of an astronaut on the moon, or a car driving through an arid canyon, or that recurring husky-like character placed in a desert or on a winding mountain road, the system generates interactive gameplay where the user can control the character's actions without losing the distinctive visual features or the overall mood of that initial reference image. This capability strongly confirms the scalability and effectiveness of their action cross-attention mechanism for open-world, real-time interactions. And critically, they highlight that this works without needing any domain-specific fine-tuning. It adapts on the fly to very different visual contexts provided by the image, which is a huge step forward for flexibility and ease of use. And finally, there's cross-domain fusion, which they highlight in Figure 13. This is where Yangen truly flexes its creative muscles, I think. It demonstrates the ability to fuse an out-of-domain reference image like, say, a photograph of a real-world desert landscape with an in-domain character description, for example, specifying that animated husky character from the training game. The system then generates an interactive video where that stylized husky character moves realistically and interacts believably within the photorealistic desert scene derived from the image. This showcases its remarkable ability to blend disparate styles and interactive mechanics flexibly, guided purely by the user's prompts. It opens up possibilities for incredibly imaginative and unique interactive content. Imagine being able to combine your favorite cartoon character with a real-world setting you just photographed yourself and then actually play in it. That's the kind of potential we're talking about.
Multi-granularity interactive editing.
Okay, this is already mind-bending. Generating entire interactive worlds from text or images is one thing, but Yan goes even further, introducing Yan Edit, the ability to edit those worlds dynamically during the interaction. Now, this concept of editing an interactive video in real time, that sounds orders of magnitude more complex than just tweaking a conventional pre-rendered video file in Adobe Premiere or something. What makes interactive video editing such a unique and difficult challenge? Why isn't it just a simple extension of the video editing tools we already have?
Yeah, it's a fundamentally different beast. The main challenge, and what makes it so much more complex than standard video editing, is the absolute necessity of maintaining interactivity and consistency of mechanics. In static video editing, you're essentially just manipulating pixels on a screen. If you edit a car in a pre-rendered video, changing it from blue to green, that's purely a visual change. The underlying reality of the video, how that car was originally simulated or filmed, isn't affected because it's already fixed. But in an interactive game or a dynamically generated world, if you change the visual appearance of that car from blue to green using an edit command, it still needs to behave exactly like the original blue car was supposed to behave according to the simulation engine. Its physics, how it accelerates, brakes, handles turns, interacts with the road, its collision detection properties, and its responsiveness to user input must all remain perfectly consistent with the underlying mechanics defined for that object type. Traditional video editing methods have absolutely no mechanism to ensure this. They treat visuals and mechanics as completely intertwined. Yan Edit has to somehow fundamentally disentangle these two layers, the visual appearance and the underlying interactive behavior, which is a huge conceptual and architectural hurdle to overcome.
Right, that disentanglement is key. And what's fascinating here is how Yan Edit supposedly solves this. You mentioned it uses a kind of hybrid model approach. Can you elaborate on how this architectural innovation actually works? How does it manage to keep the physics and the interaction consistent even when the visuals are being dramatically altered on the fly? How do they achieve that separation without completely breaking the illusion of a cohesive world?
This disentanglement is absolutely the core architectural innovation of Yan Edit. And it's designed precisely to ensure that editing the visuals doesn't inadvertently break or alter the underlying interactive mechanics. It proposes a hybrid model, which they illustrate quite nicely in Figure 14 of the picture. This model explicitly separates the process of interactive mechanics simulation from the process of visual rendering, two distinct jobs. So, the core concept underpinning this separation begins by extracting a depth map for each frame of the interactive video. Now imagine a depth map as a kind of grayscale image where typically whiter pixels represent points closer to the viewer, and darker pixels represent points further away. It effectively captures the 3D geometry of the scene. What's crucial about the depth map is that it retains the essential 3D structural information of all the objects within the scene, their shapes, their sizes, their positions relative to each other, but it completely removes all the visual rendering information. Things like color, texture, material properties, lighting, and shadows. It's essentially a pure structural representation of the world, almost like looking at a wireframe model or a clay render. Okay, so once they have these depth maps, they introduce the first specialized module, the Interactive Mechanics Simulator. This module's sole purpose is to learn and simulate structure-dependent interactive mechanics based only on these depth maps. It actually leverages the previously discussed Yan Sim model as its base, inheriting its high-fidelity simulation capabilities. Given an initial depth frame, this simulator autoregressively generates the next consecutive depth frame. But critically, its prediction is conditioned on two things. First, the user's per-frame action signals, like keyboard input telling a character to move forward, and second, new structured text prompts provided by the user. To handle these structure prompts, a dedicated text cross-attention layer is inserted into the simulator's architecture, specifically after the action cross-attention layer. This carefully designed architecture allows the simulator to learn a more generalized set of interactive mechanics that fundamentally depends on the detected structures of objects. For example, this shape is a ramp, this shape is a wall, rather than their superficial visual properties like color or texture. So a door, regardless of whether your style prompt later makes it look like red wood or shimmering blue glass, will still behave like a door according to this simulator because its underlying depth structure remains door-like. Then finally, there's the second specialized module, the Visual Renderer. This module's job is solely responsible for taking the sequence of structurally accurate depth frames generated by the Interactive Mechanics Simulator and bringing them to life visually, making them look good. It leverages Yangen's powerful generative capabilities to do this stylization. The depth frames generated by the simulator are injected as a strong conditioning signal into the Yangen model via a control net. As we touched on, a control net acts like a plugin, allowing you to add extra spatial conditioning information, like a depth map or edge map, to guide a large generative model like Yangen without having to retrain the entire base model. It steers the visual output to match the provided structure. Users then control the final rendering style, the colors, the textures, the overall artistic aesthetic via separate style text prompts. So you have this elegant separation. One part of the system, the simulator, handles how things behave based purely on their shape and structure, responding to action and structure prompts. The other part, the renderer, handles how things look, responding to style prompts while being guided by the structures provided by the simulator. They work independently but in perfect sync, frame by frame, to create a cohesive, interactive, and editable experience. It's like having a dedicated physics engine running on depth maps and a separate controllable style engine painting over the results.
Okay, so these specialized components clearly have very distinct roles. That separation seems absolutely brilliant for tackling this problem. How are they each trained then to perform their specific tasks so well? And then critically, how do they interact seamlessly in real time to allow for this dynamic, on-the-fly editing of both structure and style? What does the workflow look like during actual use?
Right. The training and the real-time inference process for Yan Edit are carefully orchestrated to facilitate exactly that dynamic, multi-granularity editing without breaking the interaction. First, let's look at the simulator training. The main goal here is to teach the interactive mechanics simulator to learn high-fidelity interactive mechanics simulation, but operating only on depth maps, not full-color images. Those structure prompts, which describe the scene's structural elements like rotating platform, wooden door, wall, are deeply incorporated during this training. To get good structural descriptions for training, they segment their interactive video data into chunks, 81 frames each, and use that powerful vision language model, Qwen 2.5 VL, again. This time they use it to perform a three-dimensional structural decomposition of each scene, categorizing the elements present into things like dynamic objects, static wall structures, and environmental platforms. These categories become the basis for the structure prompts. The actual training protocol for this simulator then mirrors the process used for Young Sim. They start with VAE training specifically for depth maps, using a variant called DepthFM. Then they simultaneously train both the action and the text cross-attention layers to handle user input and structure prompts. And finally, they freeze the text attention weights and fine-tune only the action ones for a bit longer to boost the consistency and fidelity of the interaction simulation. Next, we have the visual renderer training. Now, interestingly, instead of going through a full-blown, resource-intensive Yangen training process specifically for this renderer, they made a rather efficient discovery. They found that directly combining a pre-existing pre-post-training Yangen model, one that had already gone through the efficiency stages we discussed earlier, with readily available open-source control net weights, specifically from a model called VAE, trained for depth-to-image tasks, could already perform versatile and temporally consistent style, rendering directly onto the depth frames generated by their simulator.
Oh, so they could sort of plug and play existing components?
To some extent, yeah. It saved them a huge amount of bespoke training. So their main task here was primarily to distill this combined model, Yangen plus ControlNet, into an even faster few-step causal model, following the same post-training methodology used for Yangen itself, using DMD and self-forcing. To generate the necessary depth video data for this distillation process, they cleverly use the already trained interactive mechanics simulator. They just feed it random inputs, random initial depth maps, random sequences of action signals, and random structure prompts to get it to produce a diverse dataset of depth-only interactive videos. The style prompts used during this distillation phase are also deliberately made very diverse. They include both in-domain style prompts, like those extracted from Yangen's original training captions related to the game's art styles, and also out-of-domain style prompts, which they actually generated using GPT-4 to cover a much wider range of artistic looks. This diverse set of style prompts aims to significantly improve the open domain style rendering ability of the final distilled renderer model, making it capable of mimicking many different visual aesthetics. Okay, so that's the training. Finally, for real-time inference, when a user is actually interacting, YunEdit generates potentially infinite-length videos autoregressively and interactively, frame by frame. The process flows like this. Given the current depth frame, the interactive mechanics simulator takes the user's latest action input and any active structure prompts, and it computes and generates the next depth frame, representing the updated structure of the world one time step later. This newly generated depth frame is immediately passed over to the visual renderer. The renderer then applies the desired style rendering based on the user's currently active style prompts, producing the final, fully rendered video frame that the user sees. Every generated frame, or rather its key intermediate representations, is stored in that KV cache we talked about earlier. This is crucial for ensuring temporal consistency across the ongoing video, preventing flickering or jarring visual glitches between frames. And because this entire process happens frame by frame, it means the user can input new structure prompts or new style prompts at any moment during the interaction. The system just picks up the new prompt for the next frame calculation, allowing the content or the visual style of the world to be altered dynamically and pretty much instantaneously on the fly. The detailed inference strategies for the simulator and the renderer naturally follow the efficient methods developed for YanSim and Yangen, respectively, ensuring the whole loop runs fast enough for real-time interaction.
This sounds incredibly powerful. Honestly, like the ultimate creative tool for interactive experiences. Can you give us some vivid, concrete examples of how users can actually leverage this? How can they dynamically edit both the structure of the world and its visual style in real time within these interactive environments? Paint us a picture of what this truly enables for users sitting down with YanEdit.
Absolutely. The evaluation results they show really highlight this versatility in dynamic editing, allowing for changes on multiple levels. So, for structure editing, users can dynamically create entirely new objects or completely replace existing content within the scene, literally changing the physical layout of the world as they play. Imagine you're playing, right? And you encounter an object described by the structure prompt, rotate plat. Maybe it's a simple rotating platform. With the new structure prompt typed in by the user, like replace with wooden door, YanEdit can instantly transform that rotating platform into a static wooden door, right there in the middle of the interaction. The system processes that text prompt, alters the underlying structural element represented in the depth map, and critically, the interactive mechanics simulator ensures this new object now behaves like a door. It's static, maybe eventually openable if they added that mechanic, not like the original rotating platform. Its function changes with its structure. It can also generate new elements to address, say, obstructive structures. For example, if a solid wall is blocking your path, a clever structure prompt like create archway in wall could potentially generate an opening, enabling dynamic environmental modifications that respond directly to your needs or creative ideas in real time. This is really about changing the functional elements, the geometry and physics-relevant parts of the world as you interact with it. Then there's the equally impressive style editing. This is all about transforming the visual aesthetic, the colors, the textures, the lighting, the overall mood of the scene, without affecting the underlying structure or mechanics. Imagine starting an interactive session in a world rendered with, say, a soft bamboo and watercolor style. It looks peaceful, maybe painterly. Then at a specific moment, maybe you type in a new style prompt. Change to purple glass and cyan light. Instantly, the environment morphs visually. Everything, the platforms, the character, the background, is now rendered with this futuristic, glassy, neon-lit aesthetic. The shapes are the same, but the look is totally different. Later, perhaps you get tired of that and switch again, maybe to render as snow and soft pastel shading. And suddenly, the same structures are transformed into a cozy, stylized winter wonderland. What's truly remarkable, and the core achievement of Yan Edit, is that it renders the video content in these incredibly diverse, open domain styles, while ensuring the underlying interactive mechanics remain accurately simulated by that separate interactive mechanics simulator operating on the depth maps. So your character will still slide realistically on a surface if that surface's structure implies slipperiness in the simulation, even if the visual style prompt has rendered it as soft pastel snow instead of glassy neon. The behavior is consistent, only the look changes. This provides seamless, real-time style transformation without compromising the core interactive gameplay. It's like having both an infinitely flexible art director and a reliable game designer on call, instantly reskinning and sometimes even restructuring the world based purely on your textual commands as you play. V, the road ahead, limitations and future directions.
Okay, Yan is clearly a monumental achievement. It's pushing the boundaries of interactive AI in some really profound ways. But, with any cutting-edge technology, especially one this complex, there are always going to be current limitations, right? Areas where further technical advancements are still needed. What are some of those known hurdles for Yan? And perhaps what might the researchers be wrestling with behind the scenes that maybe isn't fully detailed in the paper, technically speaking?
Absolutely. Well, Yan represents a really significant leap forward. It's definitely important to acknowledge that several limitations still exist, and these limitations naturally point towards promising avenues for future technical advancements and research. First, maintaining perfect visual consistency over very, very long video durations still remains a challenge. While Yan performs remarkably well compared to previous methods, especially with the hierarchical captioning, ensuring absolutely flawless spatial and temporal consistency in extremely complex, dynamic, and rapidly changing interactive scenarios, especially over, say, hours of continuous gameplay, likely still warrants further improvement. The compounding nature of these autoregressive generative models means that even very subtle visual inconsistencies or artifacts, if they occur, can potentially accumulate or become more noticeable over extended periods. It's like a tiny error in a hand-drawn animation frame that becomes more apparent when you watch the full sequence. Achieving perfect long-term stability is hard. Second, there's the practical consideration of hardware accessibility. Yan's impressive high-fidelity, real-time performance, particularly for Yan Sim running at 60 FPS and Yan Genetic needing multiple high-end GPUs for smooth performance, currently relies on pretty powerful hardware. They specifically mention NVIDIA H20s, which are serious data center GPUs. This necessarily limits the accessibility of this technology for a broader range of users, researchers, or developers who might have less robust hardware setups. This points to a clear and ongoing need for developing more efficient model architectures, better quantization methods, and more advanced optimization strategies that could allow similar capabilities to run effectively on lower resource consumer hardware or even edge devices in the future. Democratizing access to this kind of generative power is a key challenge. It's a fantastic showcase now, but making it ubiquitous requires more work on efficiency. Third, the action space complexity is still somewhat bounded, inherently. While Yan demonstrates strong generalizability to various visual styles and scene types, both in-domain and out-of-domain, the underlying action space and the complexity of the interactions it can simulate are still fundamentally derived from, and limited by, the training environment that game Yuanmeng Star.
This might restrict its direct extensibility to certain real-world applications where the required action dynamics are entirely different or are far more nuanced and complex than what's typically present in a platformer-style game. For example, trying to use this exact framework to simulate complex robotic manipulation tasks requiring fine motor control might require a fundamentally different understanding of physics and interaction dynamics, and likely different training data. And finally, related to editing, while the editing control via text prompts is powerful and versatile, it's still primarily reliant on textual descriptions for both structure and style. Enhancements that allow for more intuitive and perhaps broader user control could be beneficial. Maybe incorporating visual interfaces like allowing users to roughly sketch a shape they want to generate, or directly select and manipulate objects in the scene, or utilizing other modalities beyond just text, could make the editing process even more user-friendly, faster, and potentially more creatively expansive. Imagine being able to just draw a rough shape to generate a new platform, instead of having to describe it perfectly in words.
Those are all really important points. So if we connect this to the bigger picture then, looking ahead, what are the key areas the researchers themselves are likely looking to explore next? How do they plan to push this technology even further, building on this incredible foundation that Yan provides? What's potentially on their roadmap for the future of interactive AI?
Based on the paper and the general trends in the field, the researchers are clearly looking to build upon Yan's strong foundation. Future work seems focused on roughly three main directions, aiming to overcome those limitations we just discussed and significantly expand the technology's capabilities. The first direction is inevitably scaling and efficiency. This involves pushing things further by scaling both the dataset size training on even more diverse and larger amounts of interactive data and potentially the model capacity itself. As these models get larger and are trained on richer data, their capabilities often improve, leading to better consistency, generalization, and complexity handling. But concurrently, and perhaps even more importantly, they need to continue focusing on improving efficiency. This means developing novel architectures, more aggressive optimization techniques, better distillation methods, anything to tackle that hardware accessibility challenge and make these powerful models more practical for wider deployment across a broader range of devices, not just high-end servers. The second major area is real-world generalization. This is arguably the most ambitious and potentially transformative direction. The goal here is to extend the prompt controllability and interactive generation capabilities demonstrated within game environments to actual real-world domains. Imagine being able to generate interactive simulations of real-world physics, or create editable virtual replicas of real places, or train robots in dynamically generated environments that accurately mirror the complexities of our physical world. This would open up entirely new applications beyond just entertainment and gaming, potentially revolutionizing fields like robotics, autonomous systems development, architectural visualization, or advanced simulation for training in hazardous or complex real-world scenarios. However, achieving this level of real-world generalization is a massive challenge. It would likely require entirely new data collection methodologies. Capturing real-world interactions at scale is hard. Significantly different modeling strategies to handle the inherent complexities, ambiguities, and unpredictability of the real world, which is vastly more complex and less structured than even the most detailed game environment. And the third key direction is developing richer evaluation protocols. As this kind of interactive AI-generated content becomes more sophisticated, more immersive, and potentially more integrated into various applications, traditional technical metrics like frame rate, resolution, or maybe even perceptual scores like LP-IPS may not fully capture the quality, the usability, or the overall effectiveness of the user experience. So future work aims to develop more comprehensive evaluation methods. This means going beyond current metrics to perhaps incorporate deeper analysis of human perception, task completion success rates in simulated environments, measures of long-term coherence, robustness to unexpected inputs, and even within the technical scope, aspects like ensuring reliability, safety, and predictability in AI-generated interactive content. This ensures that as the technology itself advances rapidly, our ability to rigorously measure, understand, and guide its development also evolves in lockstep, beyond just looking at the raw pixels per second.
Well, what a journey through Yan today. We explored this foundational framework that really does seem to unify high-fidelity real-time simulation, prompt-controllable multimodal generation, and this incredibly flexible multi-granularity text-driven editing. It's such a coherent, integrated approach. It feels like it's fundamentally changing what's possible with interactive AI, pushing us into a genuinely new era of digital creativity, not just for games, but potentially far, far beyond.
Absolutely. Yan is clearly charting a fascinating path for the next generation of open, creative, AI-powered digital worlds, media, and entertainment. It really shows us a glimpse of a future where our digital environments might become as fluid and responsive as our own imaginations. And this raises, I think, an important and maybe provocative question for you, the listener, to consider. How might this ability, the power to instantly generate and modify entire interactive digital worlds on the fly, potentially at AAA quality, how might that fundamentally change how we even conceive of things like storytelling, entertainment, education, or even simulation training? Would entirely new forms of interaction, creativity, or learning become possible when the world itself is no longer static, but fluidly responsive to our imagination and our actions in real time?
It's a fantastic thought to end on. Thank you so much for joining us on this deep dive into the intricate technical details and the truly fascinating implications of interactive video generation with Jan. For more cutting-edge AI and ML research explorations like this one, be sure to visit neuralintel.org and subscribe to our YouTube channel. We look forward to exploring the next big breakthroughs in AI with you.